An application we are going to talk about for these improper integrals is something called capital value of an asset. It has a relation to just present value, which we've discussed previously, and it is the present value of all future net earnings of the asset. And that'll hopefully make more sense when we look at an example, but let's get that definition down. It's the present value of all future earnings, net earnings, of the asset. And really it is just present value. If you recall, we had a present value integral from 0 to t, f of x e to the negative rx dx. All that's happening here, though, is instead of looking at a finite amount of time, we are talking about something forever, so indefinitely. So the only change that's going to happen here for capital value is instead of having a t as your upper limit of integration, you're going to have an infinity. We're still given a function that gives us our annual rate of earnings. We're still e to the negative rt dt. So we are putting this in terms of t versus present value. We had equations in terms of x, but there is a big similarity there. R is the annual interest rate compounded continuously in decimal form as usual. So let's just look at a setup and then we'll actually look at an example as well. So it says an apartment complex has an annual rent of $40,000 paid in perpetuity. That just means, indefinitely. It's going to keep earning this income. Find the capital value of this property and an interest rate of 5% compounded continuously. So let's just look at the setup because I think you could do the integral fine. Since this is a constant rate of income, we'd be looking at just a constant function of 40,000. So if we wanted to calculate the capital value here, we would take the integral from 0 to infinity of 40,000 e to the negative 0.5 t dt. So you would start that, with limit as b approaches infinity and do that replacement of the infinity like we have been doing. We're going to actually work one out on the next page. So this is actually a capital value type of situation. It doesn't explicitly state capital value, which is why I kind of wanted to do this one and work this one out. Suppose you wanted to establish a scholarship at your school awarding $8,000 a year to a deserving student. If the annual interest rate is 6.25% compounded continuously, find the amount you would need to invest to fund this scholarship indefinitely. So again, this is related to present value because it is a chunk of money you are putting in now in hopes to get a specific output per year. So it does have to do with capital value. It has to do with present value. You need to realize what's happening here is you have a desired output. Your desired output is the 8,000. So you could, talk about it as being your desired output of 8,000. And just to rewrite the capital value here, we're going to fill in 8,000. We're going to fill in the interest rate we can earn. And we're finding that present value. Okay, so let's look at what we have here. So We are going to be looking at calculating the integral from 0 to infinity of 8,000 e to the negative 0.0625t dt. Right, our rate was 0.0625. So before you start doing anything, right when you see an infinity involved in an integral, you change it to a limit. This is an upper limit being infinity, so I'm going to replace it with a b, take the limit as b goes to infinity. And we've been seeing a lot of this e raised to an exponent in terms of integrals. So we will see that once again here. So the limit as b goes to infinity, as I integrate here, I'm going to write it as, I'm going to do the 8,000, and I'm going to have e to the negative 0.0625t, and as we know, it's also 1 over that in the front, or you could just have it over, the whole thing is a single fraction, either way. And that's going to be evaluated from b to 0. So I always like to test if this division comes out decent or not. If it doesn't come out nice, I just leave it as a fraction. If it does come out nice, then I simplify it. In this case, this is negative 128,000, but it's a nice value, so I will go ahead and do that replacement there. Negative 128,000 e to the negative 0.0625t from b to 0. So plugging in the b gets us negative 128,000 e to the negative 0.0625b minus negative 128,000 e to the negative 0.0625 times 0. So a little simplifying, this is going to become a plus. This over here is e to the 0, so that's 1. And maybe it'll be more helpful to see this limit. Maybe on this left-hand side, it'll be more helpful to see it as negative 128,000 over e to the 0.0625b. Sorry if the b looks like a 6, it's a b. Plus 128,000. The reason I was just showing you that is if you notice that that negative exponent drops it to the denominator, maybe it'll be a little simpler to evaluate the limit, right? If I'm taking the limit as b goes to infinity of that negative 128,000 over e to the 0.0625b plus the limit as b goes to infinity of a constant. That one on the left, that denominator, that 0.0625 multiple doesn't really matter because that b is getting increasingly larger and larger and larger and larger, which means e to that power is getting larger and larger, which means this entire limit is going to 0. The negative on the top doesn't affect anything. Still, that number is just getting closer and closer to 0. Limit of a constant is a constant. So if you wanted to establish this scholarship and have it keep giving out that $8,000 per year, you would want to invest a lump sum now of $128,000. And the idea is as you award that money out, you still have that chunk of money that's earning interest as you are distributing that $8,000 per year.